This will be Faris, and I will be doing 6.3 for Chem. Which of the following steps can be used to separate the components of a mixture of salt, iron, and water? So salt it is soluble in water, so water would have dissolved the salt. So we would have first filter the mixture to separate the iron. So filtering the iron out of the solution, and then distilling the water to get the salt alone and the water alone. So filtering the salt out of the solution, we can't filter out salt, it's soluble. Filtering the iron out, yeah, we do that using magnet to remove the water. We can't remove the water using a magnet. Distilling the water, yeah, when we do distillation, the water will be the distillate and the salt will be left over. Using selective solubility to separate the iron, we don't separate the iron from the salt. A mixture that can be separated by filtration, as we said before in previous AMSs, to use filtration, it has to be an insoluble solid and a liquid. So when you put it in the filter paper, the sand, for example, will be a residue, and then the water falling that passed through will be the filtrate. So can be separated using filtration is a sand and water mixture. A mixture that can be separated using selective solubility, sand and sugar. We can put water to dissolve the sugar and the sand wouldn't dissolve, and then filter it out. So in this question they want for part A, they want the best technique to separate sand from salty water. So sand, we know that it is insoluble in water, so we filter it out. And the best technique to separate copper sulfate from its solution, to separate copper sulfate from the solution, we always use crystallization. Some heat is supplied to a mixture of solid iodine and salt. So we're supposed to know that iodine just sublimes from solid to gas, and the salt will remain a solid, so that's how you separate it. And for sublimation, you can't just memorize all of them, all of the solids that sublime, so you can do the process of elimination. So sugar and salt, we can use selective solubility. Ethanol and water, fractional distillation. Oil and water is fractional, not fractional. Sorry. For oil and water, we can use a separatory funnel to separate two immiscible liquids. For cartridge ink, we can use paper chromatography, so the only one we don't know is ammonium chloride and sugar, so we use sublimation. Circle the setup to separate mixture of ethanol and water. So we know على طول that ethanol and water we use fractional distillation because they have very alike boiling points. And underline the setup that is used to separate a mixture of oil and water. We can know that oil and water are immiscible liquids, meaning that they don't dissolve in each other. So we use a separatory tunnel B. NO2 has a brown color. Adding charcoal to the gas mixture that contains NO2 causes the brown color to disappear. Now we know that charcoal isn't an absorbent, it's an adsorbent. So instead of being like a sponge and absorbing everything to the inside, charcoal just absorbs everything to the surface of it, not inside it, no, to the surface of it. That's an adsorbent. So it absorbs to the surface, not absorbs to the inside. So charcoal absorbs the NO2, and we can remove anything from an adsorbent by heating it. So the NO2 can be removed from the charcoal by heating. So we can tell that the technique here, the separating technique used here is paper chromatography, because they tell us the distance traveled upwards and the mixtures. So the technique used is chromatography. Mixture 1 contains, we know that if it travels the same distance, then it has the same component. So mixture 1, its component travel the same distance as A and going up until C. So mixture 1 contains A and C. Mixture 2, it traveled until first one until B, and then it went up until C. So mixture 2 contains B and C. وبعدين mixture 3 it traveled up until A and then traveled up again until B. So mixture 3 contains A and B. A mixture of salt and sugar can be separated by selective solubility. Yeah, we know it's selective solubility. We can put alcohol to dissolve the sugar, to dissolve one thing, not the other. So it's selective solubility. A mixture of sodium chloride and ammonium chloride is separated using sublimation. What I realized is when it's chloride, a lot of the time it's sublimation. So just know that it's sublimation. Or if it's something that you don't know, put sublimation if it doesn't work for anything else. Liquid air is separated using fractional distillation. We're supposed to know this علشان all of the gases when they're liquid they'll have very similar boiling points. Kerosene and water are separated using a separatory tunnel because they're two immiscible liquids. They can be separated using a separatory tunnel. Now this is chapter 6.2 for Chem again. Which of the following are true about pure water and salty water? Now we know that when you add a solute to a pure substance, it increases the boiling point and decreases the freezing point. So the salty water solution boils at a higher temperature than pure water. The salty water solution freezes at a lower temperature than pure water. Pure water has only one boiling point, not two. The salty water solution leaves a solid residue after boiling. Yeah, because after boiling, the volume of the water decreases, leaving a bit of salt at the bottom. The concentration of the salt does not affect the boiling. No, it does affect increasing it. A student was given 3 unknown tubes and was asked to identify which tube contains pure CuSO4. Which of the following is done to identify the test tube that contains pure copper sulfate? By measuring the melting point, he can measure the melting point to see which one is the pure substance, not by measuring the concentration or moles or mass. Which of the following are alloys? Alloys, we know that they are solid mixtures of metals, so bronze and steel. Sugar water is a solid liquid solution. Air is a gas solution. Distilled water is pure liquid. A solution is heterogeneous with respect to change of phase. However, a pure substance. So what they mean here is the heterogeneous. You can literally see two different substances, while in a homogeneous mixture you can see one substance. At the same pressure, a pure substance has a fixed boiling point, while a solution has a variable boiling point. Yeah, from the previous question we know that that pure substances have a fixed boiling point, while solutions have a variable boiling point. The boiling graph of a pure substance would look something like this. It would start boiling about here, and then it would have a constant temperature, while a variable, it would start boiling around here and then increasing temperature all around. Alloys are example of solid solution, while dry air is an example of a gaseous solution. A solution is a homogeneous mixture. Yeah, a solution is, for example, water and salt dissolved in it, so you can't see the salt anymore, so you can only see one phase. So it's a homogeneous solution. And a solution, as we said, you can only see the solvent, you can't see the solute it's dissolved in it, that's salty water. And consider the following graphs. In the given graph, they want the pure substance. So as we know, uh, as I said before, the substance will the temperature will keep increasing until the boiling point, وبعدين it will continue with a constant temperature, not increasing, not decreasing temperature. It will continue with the same temperature. So graph C, this one represents a pure substance. Name the substance. So we can tell that the boiling point here is 100 علشان it is on the same line. The substance that we know that boils at 100 degrees Celsius is water. So you can say water or pure water, they accept both. So bronze, we said it's an alloy. An alloy is a solid solution. Ice water, it's just water, so it's a pure substance. Air is a gaseous solution, and so is hydrogen and helium gas. So Ne gas, or neon, if you look in the periodic table, you'll find it in group 8. So it is a noble gas, it doesn't bond to anything, not even itself, so you'll find it as atoms in the air. Just like this picture, just single atoms in the air. While Ne and Xe mixture, they're both noble gases, but they don't mix together or form compounds. But again, you'll just find each atom separated alone, not bonding to anything. Water, we know that water is H2O, so we have one H and two O bonded together to form a molecule in like a Mickey Mouse shape. And then we have an alloy. An alloy is solid and its solution, this is the only solid we have here anyways يعني, فit's just solid. And nitrogen gas, nitrogen is a diatomic, it comes in two atoms of nitrogen bonded together, just like these two, that's why it is like this one. You can tell all of these from a periodic table if they're noble gases or they bond to each other, or يعني most gases are diatomic anyways except the noble gases. Now this is section 6.1. Which substance has particles with the highest potential energy? So when we're talking about the highest potential energy, it's always about the gas particles. Gas particles have the highest potential energy. So oxygen gas and water vapor. Liquid iodine, it's liquid, so it's not the highest, or sodium, or solid, or a ribbon, magnesium ribbon, solid again. Consider the following phase change. NaCl plus heat produces NaCl liquid. Here the heat is in the reactant side, so it is an endothermic reaction and it absorbs heat. If it was an exothermic process, the heat would be in the product side instead of the reactant side. And the same thing for if it were to release heat. And it's not breakdown, it's just a phase change. 115 grams of ethanol, C2H5OH, is placed over heat to boil. Given molar heat of vaporization of ethanol plus 38.6 kilojoules per mole. So first we want to find, they want us to find the moles. So N equals M over M. the mass is 115 over C2 12 plus 12 H5 plus 5 plus O 16 plus H again 5, and you put it in the calculator. Put it in my calculator, you get 5 over 2 or 2.5. They want three significant figures for 2.50 moles, and then they want the amount of heat, so 2.5 moles times 38.6 kilojoules, you get 96.5 kilojoules. Sodium chloride vaporizes according to the equation below. Choose the correct answer to complete the following sentences. The boiling point of sodium chloride is, I don't really remember the options, but they were like this 1465, and then something 100 I think, and then 5. فيعني they wanted it not exactly, but it is the greatest boiling point because 100 is for water and it takes more heat to boil NaCl or salt than water, so 1465. The amount of heat needed for 5 moles of NaCl, you multiply the 170 times 5, you get 850 kilojoules. A substance is supplied with heat and starts to boil. Drag and drop the correct answer to complete the following sentence. At the boiling point, the temperature does not change. We said before that at the boiling point, here, the temperature does not change. It continues with the same temperature, but the potential energy increases. In the gaseous state, especially. In the gaseous state, it increases. Which of the following places would you expect water to have the lowest boiling point? Now we also know command that the more you go up, the lower the boiling point is. So at a high altitude, such as Mount Everest, the vapor pressure of ethanol at 40 degrees Celsius is 60 millimeter Hg. A closed flask containing ethanol is connected to a vacuum pump, and the pressure over the liquid is gradually lowered. If the ethanol temperature is kept at 40 degrees Celsius, ethanol will boil at. So here that we know that for a substance to boil, the vapor pressure and the pressure inside the liquid should be at this should be equal. So so we want the pressures to be equal. So they gave us at 40 degrees Celsius it's 60 millimeter Hg, and here at 40 degrees Celsius it will be at 60 millimeter Hg. The vapor pressure is in a closed container. You have the liquid here, and the vapor pressure is the pressure of the gas particles of the liquid hitting with the surface and the walls of the container. So as temperature increases, more gas particles will evaporate, so the vapor pressure will increase. To prevent superheating in the laboratory, a few boiling chips are added. So boiling chips are like, for example, you have a beaker here and a liquid, and you add these boiling chips to prevent the formation of large bubbles and overheating. Superheating, I mean. You just have to memorize it. At the normal boiling point of a liquid, the pressure is 1 atm. You also have to memorize this. It's nothing that can be explained. You just have to memorize it. And this is the video for section 6.3, 6.2, and 6.1.